Let's now take a look at graphing our trig functions, but using radians instead of degrees. So we'll start off with the sine curve. Now we know the sine curve has an amplitude of 1, so I'll mark that off on the y-axis. And I'll mark off normally it would be 90 degrees, but now I'm marking off every pi on 2 radians, but basically the boundary values. We know that the sine curve starts at the origin, so I'll plot that point in. It then goes up to the amplitude at pi on 2, and then it basically zigzags along the axis. So we'll plot in all of those particular points, and then we'll join them up with a nice smooth curve. But remember, it is a smooth curve. It's not actually dot to dot. We don't draw straight lines between them all. So there's y equals sine x. So the domain we can see is all real x. Range is in between -1 and 1. We can see the rotational symmetry, so we know it's an odd function. So that means that the sine of negative x must equal the negative sine of x. The period of a sine curve. Well, the period of a curve is how long it takes until you're back at the same point. But not just back at the same point and heading in the same direction. And so for the sine curve, that actually takes 2 pi radians for that to happen. Amplitude is 1 unit. Okay, let's do our cosine curve. Same idea, I'll mark off the amplitude that I know, so 1 minus 1, and I'll mark off all the boundary values on my axis, so every pi on 2. Now, the cosine curve, it actually starts up at the amplitude. So when x is 0, we know y is 1. It then comes down to the axis, and again we have that zigzagging pattern. Drawing a nice smooth curve, and there's our cosine curve, which essentially is the same as the sine curve, but has been shifted horizontally pi on 2 units. So that means the domain's going to be the same, all real x. The range is going to be the same, it's still in between -1 and 1. But this time you'll notice we have symmetry in the y-axis. So that means it's an even function. Now that implies the cosine of negative x is equal to the cosine of x. Period, once again, is 2 pi. And as I said before, the amplitude is 1. Well, remember I was saying it's basically the sine curve? If we use our shifting ideas, there's the translation. Cos x is the sine of pi on 2 minus x. So minus x, reflect the sine curve in the y-axis, and then the pi on 2, we shift it right pi on 2 units. Let's complete the suite. So we now have the tan curve. Now, tan doesn't have an amplitude, so I'm not going to mark anything on the y-axis, but I will mark in those boundary values again. Now, tan starts at the origin, but then something interesting happens. Pi on 2, we get an asymptote, and then that pattern repeats. X-intercept, then an asymptote. Now we sketch in our curves, and we know we always bend towards the asymptote. So I'll draw in the first section there. Remember, it's not a cubic, so you don't have it flat at the x-axis. It actually goes through at 45 degrees. And then that branch repeats itself between all of the asymptotes. Now, domain, that's a little bit harder to write. So it's all real x, but we have all these asymptotes. So the way I put it down is I'll say, well, I know the first one happens there at pi on 2, and every pi before and after, there's another one. So I'll say plus pi k, where k is some whole number or integer. The range, all real y. Now it has rotational symmetry, so it's an odd function. That means the tan of negative x is equal to the negative tan of x, and the period for tan is only pi. It repeats every pi units. Well, let's just do one of the reciprocal curves. So I'm going to do cosecant, which is, of course, the reciprocal of sine. So sine curve, I've dotted it in there in red. We want to draw the reciprocal. Reciprocal, x-intercepts become asymptotes. So all of those x-intercepts are now asymptotes. We know that 1 divided by 1 is 1. So all of those peaks, those points remain. But the other thing we know, when we turn it upside down, anything below 1 goes above 1. So whereas the sine curve was always in between -1 and 1, the cosec curve is never in between minus 1 and 1. So we end up with these series of U-shapes. They're not parabolas, they're just U-shapes. All right, well, in 11J, we'll focus on sketching some of these trig functions.